This is a video from section 4.2 in a Calculus 1 class. We're going to take a look at problem 30. Suppose that 3 is less than or equal to f prime of x, which is less than or equal to 5 for all x. Show that 18 is less than or equal to f of 8 minus f of 2, which is less than or equal to 30. So let's prove this. Since f prime of x is greater than or equal to 3 and less than or equal to 5 for all x, we know that f is differentiable for all x. And another way to say that is that f is differentiable on the interval negative infinity to infinity. If f is differentiable on the interval negative infinity to infinity, then we know f is continuous on that same interval. In particular, f is continuous on the closed interval 2 to 8. And f is differentiable on the open interval 2 to 8. This is an incredible application of the mean value theorem. By the mean value theorem, there exists a c in 2 to 8, that open interval 2 to 8, such that f prime of c is f of 8 minus f of 2 divided by 8 minus 2. Now, let's go back. We know that f prime of x is greater than or equal to 3 and less than or equal to 5 for all x. For all x. So that means we know that f prime of c is greater than or equal to 3 and less than or equal to 5. But remember that f prime of c is f of 8 minus f of 2 over 8 minus 2. So I'm just going to plug that in. And so f of 8 minus f of 2 over 8 minus 2 is greater than or equal to 3 and less than or equal to 5. 8 minus 2 is 6. So f of 8 minus f of 2 divided by 6 is greater than or equal to 3 and less than or equal to 5. So we're going to multiply through by 6. And when I do that, I get 18 is less than or equal to f of 8 minus f of 2. And that's less than or equal to 30. And that's exactly what I wanted to prove. And that's how you do problem number 30. Let's take a look at problem 31. So this is what it asks. It says, does there exist a function f such that f of 0 equals negative 1, f of 2 equals 4, and f prime of x is less than or equal to 2 for all x. Now, that's a question. So let's talk about this. Since f prime of x is less than or equal to 2 for all x, we can say f is differentiable on the open interval negative infinity to infinity. It has to be open, right? And just like in problem 30, if f is differentiable on negative infinity to infinity, then we know f is continuous on negative infinity to infinity. But what I want to do is I want to restrict my attention to the interval 0 to 2. So this is what I'm going to say. F is continuous on the closed interval 0 to 2. F is differentiable on the open interval 0 to 2. So I'm going to say by the mean value theorem, there exists a C inside the open interval 0 to 2 such that f prime of C is f of 2 minus f of 0 divided by 2 minus 0. Now, let's recall something. F of 2 is equal to 4. F of 0 is negative 1. And we're going to divide by 2. So what that tells me is that f prime of C is equal to 5/2. That's a problem. So this is a contradiction. And I'm going to explain why in a second. Why is that a problem? Because in the problem, we are given f prime of x is less than or equal to 2 for all x. And so that implies f prime of C is less than or equal to 2. But we just said that f prime of C is 5/2. And so 5/2 is less than or equal to 2. And that's false. And so therefore, no such function exists. So this contradicts the mean value theorem and its condition. Let me back out. It contradicts the condition in the problem where f prime of x is less than or equal to 2. Everything else along the mean value theorem follows really well. It's the condition that f prime of x is less than or equal to 2 for all x. That's the part that's causing us problems. And so one thing I also want to make clear in the beginning is we're going to assume such a function exists. And we're going to show that that causes issues. And everything, again, follows really well. Okay, that'll conclude this video for section 4.2, and we did problems 30 and 31. Thank you.